Hello everyone and welcome again. This is the next lecture for the NPTEL course Machine Learning for Core Engineering Disciplines, and today we will introduce the important concept of cross validation. Right? Cross validation helps us understand how robust and generalizable an ML model is. Right? Usually machine learning models are trained on certain data and then tested on unseen data. However, small variations in the test or the trained data can lead to change in the model performance. We would want to know as to how robust the model is to a slight change in the training data, and this is done by the creation of a subset of data from the training set called the validation set, and using the validation set and tweaking it slightly and tweaking the training data as well slightly, we can figure out how robust our ML model is. Now cross validation is very important because it is also useful in tuning of hyperparameters, right, which as we had discussed, they are the model configurational variables, right, and the training configuration variables which have to be set prior to the training process, right. So let us go ahead and take a dive into the concept of cross validation. So the topic for today is cross validation in machine learning. And the idea is that cross validation is a statistical approach to quantify the robustness of an ML model to changes in the training data. Okay, and it also provides an estimate of the generalizability of the ML model by considering varied test data, right. So cross validation is a very important procedure that is to be followed before an ML model can be deployed in production, right. Before in any core engineering discipline, in an industry or even in an academic setting, before you deploy an ML model, you want to understand how well it generalizes, right. So let us see how this is done. Okay, so to accomplish cross validation, which is also abbreviated as CV, a fraction of the data points in the training set are selected and made part of a validation set. Okay, so this is some new terminology that we are introducing. So there is no longer just a train and a test set, there is also something known as a validation set, which is in fact derived as a subset of the training set. The ML model is then trained using the remaining data, and by remaining data I mean the original train set minus the chosen validation set. Okay. So, the ML model is then trained on the remaining data and the validation set is used to check the model performance. Via the usual loss functions. Right. So, the loss functions we studied several lectures ago. You have to pick the right loss function and then you have to employ it in your training process along with the validation set. So, schematically this can be shown as follows. So, essentially you have a train and the test set, right. So, initially let us say this is the partition here. So, this is the train set or training set and this is the test set. Okay. And now what we are doing is we are taking a subset of this, right, and then we are using this as a so called validation set. So, the actual training takes place with this data. So, this is the actual training data, right. So, I hope visually this tells you, right, how the cross validation procedure works. At this point, although it is just validation, right, it is not cross validation because we have not sort of given every point in the training set to participate in both the training and the validation procedures. At this stage it is just simply called validation, it is not called cross validation unless every point in the training set somewhat has had a chance to participate in principle. Although in practice I mean there are techniques when you use cross validation with random cross validation with sampling, right, subsampling, and in those cases you may it may not be possible that all the points have participated in both training and validation. Okay. So, we will explain exactly how this cross validation happens. There are various strategies called k-fold cross validation and leave one out cross validation and so on. So, we will explain those a little bit later. Let us first understand why the cross validation procedure is so important, why do we need it. So, we want to understand why is cross validation needed, right. So, let us say you are a materials engineer or a mechanical engineer or an electrical or a civil or a chemical or biochemical engineer. You want to make a model. So, an aerospace engineer, they may want to predict, for example, what is the drag on an aeroplane, right, given sort of the dimensions and the flow profile and so on. And the model may be trained using some amount of training data that has been perhaps generated through a computational fluid dynamics simulation. However, before you can really use it, you have to change the training data a little bit and see how it performs. Similarly, a materials engineer who has trained an ML model to use electron microscopy images to find out more about the material structure, right, they may have to again validate the model with unseen data and give each data point in the train and test sets to participate each data in the train set to participate in the training and validation procedures, right. So, that is very important, and so therefore cross validation is needed because it prevents overfitting and underfitting by checking model performance on unseen data, right, varying the train and validation sets, right. So, it is not like you just use one validation set to understand how the model is working and therefore, you just overfit, right, to do well on that validation set. You give various, you take various validation and train sets and therefore, you prevent overfitting and underfitting. So, it is very crucial when you deploy such models. The other advantage here is that it makes efficient use of limited data, right. If you have limited data, then you can't really say that your test set or validation set is fully representative of the entire data, right. So, you have to use cross validation and make efficient use of limited data, right, while also providing reliable and stable model performance metrics. So, it is not like you will predict a really high R square or a very low MAE or MAC just because, right, you are lucky, right, your validation set proved out to be one where the model was doing well. So, your estimates of the model performance will be much more reliable and robust if you use cross validation, right. So, that is the importance of this procedure, right. So, another advantage is that hyperparameter tuning is often carried out in conjunction with cross validation. So, the cross validation provides you a way not only to understand model robustness and generalizability, but also allows you to carry out hyperparameter tuning, right, because by tuning the hyperparameters you can see what are the set of hyperparameters that give the best performance across all the possible realizations of the validation set that you are considering. Okay. So, now how is this done in practice, right. So, there are several types of cross validation which can be done. So, we will now go ahead and discuss those. So, the next topic is the types of cross validation, right. The first one I want to introduce is called a k-fold cross validation, and what happens in this method is that we partition the training set and let us say it contains n data points into k sets, right, or k folds, each having n divided by k points, right. So, if there are k folds or k sets, each of those will have n divided by k points, right, and thereafter the ML model is trained using the data in k minus 1 folds and is validated with the remaining data. Right. Thus, every point in the original training set would have participated in both training and validation. Okay. So, this k of course here is a number that you need to set, right. There are n data points and k folds. So, you need to set k. Popular choices of k are let us say k equal to 5, right. So, if you choose k equal to 5, then it is called 5-fold cross validation. Or 5-fold CV in short. You could also do lower number of folds or a higher number of folds, it all depends on how many data points you have. If you have a huge number of data points and it is not very expensive for you to train models, you can do 10-fold cross validation, but if model training is expensive, you have fewer data points, you may have to go with fewer number of folds. So, let us see how this 5-fold cross validation when k equals 5 looks like, right. So, there are 5 folds here, right, and I am going to explain pictorially what happens. So, essentially we have partitioned the data into 5 folds, right. So, 1, 2, 3, 4 and 5, right, and in the first fold, right, what it means is that these chunks, right, are used for the training and the remaining one is used for validation, right. So, T is the training data and V denotes the validation data. Okay. So, the second fold would be something like this. So, you have again, right, 5 partitions, however, the first, second, third and fifth are let us say now the training data, and then the fourth, right, set of n by k points, that is the validation data, right. So, it is important to note that each of these boxes contains n by k data, right, and in this case k is 5. So, it is really n by 5 data points, right, each of them. So, that is the second fold, and similarly you can understand, right, what will happen in the next set of folds, right. This is the second fold, you can pictorially draw the third fold, the fourth fold and the fifth fold. So, it will look something like this. Again you have the same set of 5 partitions in each case, but what differs is which data goes into training and which data is used for validation, right. So, the validation set will keep on moving. So, here the third partition or the third set will be validation, here the second one will be the validation, and here the first one will be the validation, and the remaining of course will go into the training data. Right. So, that is how each data point will get to participate in validation. So, here these set of points are participating in validation, here these sets of points are participating in validation, but the others have moved to train, right. So, that is why I was saying that every data point will get a chance to participate in training as well as in validation. So, that is the beauty of k-fold cross validation, right. And then what do you do? Once you have done all these folds, right. So, you have essentially trained k models. in this case k is 5. So you have trained 5 different models, those 5 different models will have different performance on the validation set. So you can compute the loss function of the 5 models on the 5 different validation sets, right. So what will you get? So each fold will provide a different model performance, and it depends on you what you want to use as a metric of the model performance. You know that it can be R squared, which is usually not recommended because it is I mean you can get very high R square if you have a large number of data points, or even if yeah there are some cases you will see in your homework that it is possible to get very high R square even though the data may look very different. But more recommended are things like the RMSE, MAE, mean absolute error, root mean squared error, etc. right. So each fold will perform a different, will provide a different model performance, and the average metric, right, will be computed over these 5 folds. So an average model performance will be estimated over the k folds, and this way, right, you are not really biasing your model, right. Essentially it will not happen that let us say on this validation set your model performed really well and you thought the model was good, but then when you use the second fold that validation set your model did not perform well. So the model is not as generalizable as you would have thought. So that is the nice part about k fold cross validation, right. Now there is a small tweak to k fold cross validation that is possible, that is called stratified k fold, right, and this is obviously important when your data, right, just like in classification we had to use the balanced accuracy score, right, because sometimes it happens that some classes are very highly represented in your data and other classes are not as highly represented. So you have to make sure that you are sampling properly each one according to their proportion, right. So the stratified k fold preserves the class proportions in each fold, and thus is useful in classification problems with imbalanced classes. Right. So let us say you are training a classification model and you had to perform k fold cross validation, and the data was corresponding to whether there was a defect in a manufactured product or not, and let us say that most of the products that are manufactured are good, they are not defective, and only some of them are defective. Then you have to make sure that you are sampling the data properly, right, and proportionally including number the images of the products which are good, right, which have the right quality, and images of the products which are defective. So this is done through stratified k fold, right. So now that we have finished the discussion on k fold cross validation, we will next move to something known as the leave one out cross validation. So the second way of doing cross validation is called leave one out cross validation, and it is shortened as LOOCV. As the name suggests, here you are just leaving one point out to act as the validation set, and n minus 1 points are used for the training set, right. So in LOOCV we use as many folds k as there are data points. n so that all but one points, right. So, n minus 1 points or k minus 1, because n and k are the same. So, all but 1 points are used to train the ML model, and each point, right, or the remaining point is used as the validation set. Right. So, there are some advantages and disadvantages of this. The advantage is that using a large training data reduces the bias in the models trained in each fold. Right, but increases, right, the sort of variability in the validation, because there may be outliers and some of them, right, will give rise to a very high loss function. Of course, you are averaging over all of them, right. That is the advantage in principle. The disadvantage is that you have to train as many models as there are points. You have to train n models, and if n is billion, if n is a billion, you do not want to train a billion models, that is very expensive, right. So, that is a problem. So, this approach is computationally expensive. Since n models are trained, right. So, this approach is expensive and typically should be used if model training is inexpensive. Or if you have a small data set, then you could use it. For a small data set, because then this point becomes important, right. You will have more training data which reduces bias. So, for small data sets, that is important. So, you can remember that LOOCV can be preferred if model training is inexpensive, or if you have a smaller data set. So, you need more data for training. So, this allows you to maximize the amount of training data, right. And finally, I want to introduce the last type of CV that we are considering here, and that is called the repeated random subsampling CV. So, here a fraction of data points are chosen randomly and used to train the model. while the remaining ones are used for validation. So, this procedure is repeated several times. With the advantage being that independent control over the number of repetitions or number of models trained and the train validation split. Okay. So, this method allows independent control over the number of models and the train validation split, right. It is also called Monte Carlo cross validation because of the randomness involved. There is one limitation though, the limitation is that it is not necessary that every point will function as validation and every point will get a chance to participate in training, because of the way the randomness is involved here, you do not know whether that will really happen. So, this brings me to the end of this particular lecture. In today's lecture we discussed the important concept of validation, which means that you partition the training set into some amount of training and some validation data, and when it is done in a slightly different way where various points are given chances to participate in training and validation, it is called cross validation. So, across the data set you are doing a validation procedure, and we discussed three ways of doing it, one called the k-fold cross validation, particularly 5-fold cross validation is quite popular. Then we discussed leave one out cross validation where the number of folds is equal to the number of data points, and this may be particularly useful for smaller data sets or when the training procedure is inexpensive. And finally we discuss the random subspace sampling cross validation approach, right. In the next class what we will do is we will talk about hyperparameter tuning, which is a key to develop models that are generalizable and perform well on the validation and on the test data sets. Thank you for joining today, and I look forward to seeing you next time.